So most of what I'm going to talk about is based on this paper by Anton Kapustin from 2014. And then there's also some nice notes, math notes on Cobordism, which I'm not really going to do too much with in this talk, but I just want to say that these are fairly nice and readable notes. So I want to talk about SPT phases beyond group cohomology. So we heard a lot about group cohomology. I want to go beyond that. And also, I'm going to sort of discuss the continuum space-time field theory point of view rather than the lattice, which has been sort of the way that things have been presented so far. So let me just sort of write out some of the distinctions between the lattice and field theory points of view. And then I'll sketch out the rest of my talk. So, so on the lattice, we have, for SPTs, there are symmetries that are relevant, and in all the examples we've seen so far, most of the examples we've seen so far, there was an on-site unitary representation of some symmetry group G. So this is the way that symmetry is implemented on the lattice. And there was some Hamiltonian, which was a sum of local terms. Importantly, when you define phases, the definition of phases was as equivalence classes so equivalence classes of gapped Hamiltonians under an equivalence relation that's given by finite depth circuits of local unitaries, which I'll abbreviate FDCLU. Okay, with symmetry, these circuits had to obey certain symmetry properties. And as far as SPT phases were concerned, we wanted to restrict to systems which didn't have intrinsic topological order, which were kind of nice, and that was formulated in terms of sort of short-range entangled states. So states, for the purposes of SPTs, by short-range entangled, it just means something that can be disentangled with a finite depth circuit of local unitaries. So there's this idea of short-range entanglement. Okay, so on the field theory side, the field theory approach to SPT phases, you instead deal with a continuous space-time. So it's not a lattice, it's a continuous manifold, and you deal with, rather than space-time. The way that symmetry is encoded in the field theory representation is through principal G bundles. And I'll sort of review that concept a little bit as we go through some examples. I'll also refer to these as G gauge fields. The way that you define phases in sort of the field theory approach is by, the object that you look at is this partition function. So the partition function of the theory on a manifold M, so we call the principal G bundles A. So partition function on a manifold M with some gauge field, G gauge field A. So this is like the partition function of the theory with a background G gauge field. So this is, in general, this could be anything. For SPT phases, this is a U1 phase. And that's related to the idea of a unique ground state, which is ultimately on the lattice side related to short-range entanglement. At a sort of intuitive level, the way you go back and forth between these two pictures is, if I have a lattice Hamiltonian, I can put it on some non-trivial continuous space-time manifold and couple it to a background G gauge field and compute the partition function. So those are the words that are said. And in practice, it is the case that for a lot of these models, like for instance, for the group cohomology models that Chia talked about and their generalizations to any dimensions, there is a very natural way to put those lattice Hamiltonian models on general spacetimes. Okay, so there are these lattice models in sort of state sum models on general spacetimes, and it's actually relatively easy to go from there to the continuous field theory. So this is pretty straightforward to do for certain models, but in general, it's not. So this is sort of the point of view I want to emphasize, that in general, if I just give you some random lattice Hamiltonian, it's not one of these very nice, exactly solvable, idealized models, but just some general spacetime Hamiltonian, just some general lattice Hamiltonian. It's not clear how to put it on a general spacetime. It's not clear what to do. Yeah, China.
So the A is a connection, not necessarily flat. Is that right?
Right, so in this case, I'll be sticking to discrete groups, and so these will just be flat connections.
So it will be flat.
Yeah.
So there's no dynamic. It's a classical background.
It's a classical background. Yeah. So, right, so, the point of view that I want to take here is I don't want to sort of try to rigorously define or even unrigorously define how you go from the lattice to the field theory. I just want to sort of discuss the field theory on its own. So I'm just going to give definition of SPT phases just from the field theory point of view, following this paper by Anton Kapustin. And the way that I'm going to do this is I'm going to sort of work up to this definition by looking at sort of a couple of just simple examples where we kind of know what this partition function has to look like, and from that sort of generalizing and sort of proposing some general constraints on what this partition function should be, and that's going to lead us to this Cobordism classification, which extends group cohomology. Okay, so let me look at a first example. So this is like the simplest possible thing you can do, simpler than anything we've done so far. Look at 0 plus 1 dimensions. So when I say 0 plus 1 dimensions, the plus 1 always means space time. So 0 spatial, one time dimension. This is just quantum mechanics. And take G to be on-site unitary Z2. So in this case, what are the different SPTs? I mean, this is very simple. The different SPTs, like what can you possibly have with just an on-site Z2 symmetry? Well, your quantum mechanical system could be, the ground state could be even or odd under the symmetry. So there's sort of two SPTs, the trivial SPT where it's even and the non-trivial SPT where it's just an odd charge. So this is like the simplest example of a group cohomology model. So let's take, I'll use the letter alpha to denote SPT phases. So let's take alpha to be non-trivial Z2 charge, that's sort of non-trivial SPT. Okay, so in this case, we totally understand what the lattice picture is. Now, what's the field theory picture? Well, we're in 0 plus 1 dimensions. Obviously, we're going to probe this thing on circles. So let me draw a circle. And this is simple enough that we can just sort of immediately see what all the possible principal Z2 bundles are. So a principal G bundle is just a copy of G over every point. It's a fiber bundle with fiber G. And in this case, I'm not going to give all the formal definitions, but in this case, there's sort of obviously two principal G bundles. There's one that's kind of untwisted, and then there's one that's twisted. So the solid lines sort of, the two solid lines denote the two elements in G. So twisted and untwisted. And here, okay, let me call this one A0 and this one A1. It's clear that when you have a non-trivial charge, I mean, sort of this is just at the level of intuition. If you just imagine this direction along the circle as time, it's clear that sort of this non-trivial principal G bundle is like going in time and then acting with the Z2 generator, right? This twist is just like acting with the Z2 generator. So in this partition function, you're evolving in time, in the ground state which does nothing, and then you're acting with the Z2 generator. So you're just measuring the Z2 charge. So it's clear that the action of this guy should be -1. So the manifold is S1, A1 is -1. Whereas here the action should be, the partition function should be +1. Okay, so we can write that in a more compact way by just saying that the partition function is the exponential of some effective action I'm not looking at the screen. Like, is this happening more and more often, or it's getting worse? Oh, great. I could switch to the board.
I think it's okay so far.
It's okay so far. Okay. All right.
Is there any way to plug that tablet into the projector?
Directly? Oh, maybe. Yeah. Does anybody have a connector for it? No, I think the dongle might have come with the other one.
Are you using, what kind of tablet are you using?
Well, it's QCA's tablet. I think so. Is this a Surface? No. So this is a Apple. Yeah. Okay. That'd be, yeah. Thanks. All right. Okay. Well, let me just kind of try to work with this. So, oh, now it's not doing anything.
Can I ask you a question?
Yeah, sure.
Yeah. So when in here, when you're saying it measure the Z2 generator is measuring the charge here.
Yeah.
What exactly do you mean here?
What I mean is this partition function is -1.
Okay, that's the whole meaning.
Yeah. So I'm not going to try to sort of connect the lattice formulation to the continuum formulation at any deeper level. I'm just sort of motivating what constraints I'm going to put on the continuum side. Yeah.
Sorry, is the time the circle?
Yeah.
Like, that's the time?
That's the time. Yeah.
Okay.
It's 0 plus 1 dimension, so the 1 dimension is the time dimension. There's no space dimensions. Okay. So let me just sort of write, because we're going to generalize. Let me write this action as alpha. This is simply 1/2 the holonomy of this gauge field. So here, I'm looking at this object as an element of H1, the first cohomology group of M with Z2 coefficients. Okay, so this is valued in 0 or 1. So 1/2 of that is valued in 0 and 1/2, and when you exponentiate that times 2 pi I, you get +1 or -1. Okay, so simple enough. Now let's do something slightly more non-trivial. So let's do a second example. Example 2. So let's go up 1 dimension. So 1 plus 1 dspt. Let's take Z2 cross Z2. Okay, so this is precisely going to be the SPT phase that QCA discussed. This is this Haldane phase. I'm not going to write out the Hamiltonian, but so we're going to have to define some kind of an action here. Let me just probe this theory on not all general manifolds, but let me just probe it on a torus first. So let me imagine a torus, and let's just try to guess what this action should be in this case. It's a Z2 cross Z2 SPT, so there's 2 Z2s involved, and so there's going to be 2 Z2 gauge fields. The Z2 cross Z2 gauge fields is like 2 individual Z2 gauge fields, so let me call them A and B. So I have Z2 gauge fields A and B. And so, right, so what do we know about this partition function? Well, one thing we know about it is, and you can sort of see this from the model QCA discussed, which is that if you insert a flux of one of these Z2 gauge fields, let's say a flux of B, so this is inserting a flux in space, and you measure the charge of the other Z2, so in other words, you measure a flux you measure the charge of the A gauge field, then the partition function should be -1. Okay, so these dotted lines are meant to, just because I find it difficult to draw principal bundles, these dotted lines are meant to represent Z2 principal bundles. So, the one corresponding to A gets a twist across the horizontal dotted line, and the one corresponding to B gets a twist across the dotted vertical line.
You have to tell us which direction is space and which is
for the purposes of this drawing, let's say the horizontal direction is space. I mean, this particular situation is going to be symmetric. It's not going to matter so much. But this is just one piece of information that I know should be true. Now, how do I know that from the lattice model? From the lattice model, this is something that, so this is one of those things that actually can be seen in the lattice model. From the lattice model, you can actually be quite explicit about what it means to insert a Z2 flux. The flux of one of the Z2s, you can actually do this sort of very explicitly between two of the sites, and you can sort of concentrate all the vector potential, all the gauge potential between these two sites. I mean, it's a discrete gauge field, so you kind of have to do that. But effectively, what that amounts to is acting with the Z2 generator on one of the spin-a-halves, acting with one Z2 generator on one of the spin-a-halves. And if you think about the fact that on spin-a-halves, the two Z2 generators anti-commute, that sort of inserts a charge of the other Z2. So this is sort of the expectation that you have. Again, I'm not proving any of this rigorously or anything. I'm just sort of motivating a subsequent definition. The expectation is that here, in this case, again, we're going to have the partition function be a function of these two gauge fields, A and B. This is just a single Z2 cross Z2 gauge field. Again, there's going to be an action involved. And this action, just based on this one piece of data that we have, should be something like 1/2 times the integral of A wedge B. View A and B as Z2 valued cohomology classes. Cohomology classes with Z2 coefficients. Wedge them together, it gives you a degree 2 cohomology class. You can integrate that and get, yeah, an action.
Sorry, if you want the physical interpretation of this picture, you're inserting a flux of the first gauge field and you're measuring with the generator of the second?
Yes, correct.
Okay.
Yeah. So you can work that out. I mean, I encourage you to work that out on the lattice model that you presented. That's what you will get. And there's sort of a very general prescription for how to, in space on a lattice, couple to a background gauge field that applies not just to that particular model, but to all models. So this is sort of gives an invariant of lattice models. So that's something you can do for lattice models. That's a fact about lattice models. And it's reproduced by this particular action. So that's that's one particular example. And let me just give one more example. So let's take the last SPT that you talked about with just a single Z2. Alpha is this, for lack of a better word, I'll call it the Levin-Gu phase, although there's obviously other, and Xie and Zhao Ganwen were also sort of invented this. So here, it's a single Z2, so I have only a single Z2 gauge field. And there's not a whole lot I can do, sort of based on the intuition we got from the previous two examples. The only thing that I can really write down is, I only have A, and I need a degree 3 cohomology class. So I'm just going to take A wedge A wedge A cubed. Now you might, your intuition might be this is 0, being a wedge product of one form, but with Z2 coefficients, this is not actually 0. And in particular, if you probe this theory on, if you just evaluate this action on RP3, so RP3 is a three-dimensional real projective space. There's a canonical Z2 principal bundle on it. Just imagine, obtaining this from identifying antipodal points on S3. So then it sort of naturally gives you a pair of points over every point in RP3. This is canonical principal Z2 bundle. So here, the action on this particular manifold with that particular bundle evaluates to 1/2. So that's sort of the non-trivial action. So the partition function on this manifold with that principal bundle gives you -1. So, okay, I mean that's nice, but this is like even now harder to connect to the lattice picture. Like, how do I take the lattice and put it on a space-time RP3? It's not at all clear. So towards the end of the talk, if I have time, I'll tell you about sort of how to connect the lattice to the space-time description, even for these sort of more complicated examples. But for now, let me just sort of leave that alone. Yeah.
Maybe that's a philosophical question, but so you have two different ways of thinking about things.
Yeah.
The lattice way, like the low.
Sure.
And the field theory way. Why should I believe that in general these are going to give me the same answer?
Just it seems to have worked out.
So practical.
Practical. I mean, I'll give you some more evidence right now, actually. So I'll just yeah. So the next level, as to sort of begin answering that, let me show you at least that the same mathematical structures appear both in the lattice and in the space-time picture insofar as the group cohomology phases are concerned. So she already introduced group cohomology phases on the lattice. She gave some examples in various dimensions, but let me sort of let me give the definition in the space-time context, and we'll just see that the similar mathematical structures arise. Of course, this is not at all surprising for these incohomology phases because that's how they were actually originally built. It was sort of motivated by that picture, but it's one piece of evidence to suggest that these are doing the same thing. But yeah, I mean, your point is well taken. For the beyond cohomology phases, it's absolutely not clear why this should give the same answer. And in fact, yeah, I mean, in fact, it's very tricky in certain cases to relate the lattice to the field theory. Yeah.
Is this theory that you've written down supposed to be the continuum description of the SPT or of the gauge SPT?
The SPT.
Oh.
Yeah. So the gauge field here is a background gauge field. It's a non-dynamical background gauge field that goes to probe the thing. Yeah. Okay. So right. So now let me be a little bit more abstract. To sort of formalize things a little bit, let me just introduce the formalism of a classifying space. Again, throughout this discussion, I'm going to sort of take the most convenient conditions on my group G, so finite, discrete, for now unitary, although I'll generalize to non-unitary. So a classifying space for G is a topological space BG with a certain principal G bundle on it. So this is a canonical principal G bundle. And BG is uniquely characterized by the fact that I guess it's connected, and pi 1 of BG is equal to G, and pi n of BG is 0 for n greater or equal to 2. Okay, so and in fact, there's a very explicit construction you can make of BG as a cell complex, but that's not really going to be necessary for what I'm going to discuss. The important property of BG, this classifying space that I'm going to use, is that it's sort of a warehouse of all possible principal G bundles. So in other words, no matter how, if you have some complicated manifold M, and you have a principal bundle, G bundle A on M, so for any such M and principal G bundle on M, there exists a unique up to homotopy map from M into BG that pulls back that particular principal bundle, such that A is equal to the pullback. Okay, so this is the principal bundle. I'm calling it pi, I guess. So in other words, principal bundles on M, which are the things on which we want to evaluate this partition function, are the same things as maps into BG. Okay, and so what does that buy us? Why is this a sort of useful abstraction? Well, it just says that instead of the bundle itself, we can sort of work with the homotopy classes of maps into BG. And we can use those maps to obtain actions. Okay, so given now any, let me call it, okay, so let's say this M has dimension D. So now given any x in the D cohomology of BG with coefficients in R mod Z, physicists like to call this U1. Given any x in this D cohomology of BG with R mod Z coefficients, I can define the action associated with the principal G bundle A to be just the integral over M of the pullback of x. Okay, so remember, A determines F, and then I use F to pull back X, and I integrate it, and that gives me an action. Yeah?
So is alpha is F star of which?
A is F star of pi, so A is the pullback of the canonical principal G bundle pi, this pi. So there's, so the nice thing about this perspective is that, BG is fixed once and for all. This pi is fixed once and for all. It's just the principal one. And then every G bundle that you might possibly want to use to probe the theory on M can be obtained by pulling back this principal bundle using some map, and that map is unique up to homotopy.
Okay, so the principal bundle is in the classified in BG.
Yeah, there's a principal bundle in the classifying space, but then the map F from your spacetime manifold into the classifying space allows you to pull that bundle back to the spacetime manifold. So, yeah. So every bundle, and so every possible bundle on the spacetime manifold you want to probe is given by pulling back something, and that F is unique. And so so this is nice because this allows you to construct all sorts of actions of this form, and this mathematical structure, the Dth cohomology group of BG with U1 coefficients, this is precisely group cohomology. So this is precisely, the objects in there are precisely these group cohomology classes that QCA defined. Okay, and so, okay, so all I've given you is, well, okay, yeah. So yeah. Let me maybe just end there with the abstract stuff. Oh, there's one more thing I want to say, which is how anti-unitary symmetries are represented. So actually, maybe let me pause for questions. So questions, yeah.
So sorry, how does this X relate to the canonical bundle power?
X is just a cohomology class in BG, so it doesn't really directly relate to pi. Pi is used to determine F. So the way, well, sorry, A is used to determine F.
Oh, okay.
But you can sort of forget about pi. It's.
So the relationship is the A on the right-hand side is telling me what F to use to pull that X.
Exactly. Yep. So these are called characteristic classes of the bundle. So this sort of formalizes the examples that I gave so far. Yeah.
So does this mean A is in the trivial class?
Why would A be in the trivial?
Just because of the pullback of the principal. No.
So A is a principal G bundle on M.
Sorry. I guess the pi is in the trivial class in HD.
Sorry, say again?
Is pi the trivial element in HD?
Pi, this pi, is a principal G bundle on BG. So it's not a cohomology class. It's a principal G bundle on BG. Okay, so this is a very formal picture. I'm not necessarily going to use it too much. I just wanted to put it out there to illustrate that these mathematical structures, these cohomology groups that QCA talked about, sort of obtained from this lattice context, turn out to be the same things as this. I didn't prove this. I don't have time to prove this, but it turns out that if you work out the cohomology groups of BG, you get precisely the same mathematical objects as the ones that arose in QCA's lattice construction. So that's yeah.
Here, so there are no background field here. There are no flat connections in this picture, right?
No, the A is a background flat G gauge field.
I thought that the vision A is the principal bundle right now.
Yeah, it's the same thing, right?
Oh, I think I know what's going on. So there's also a fundamental group map. That's the flat connection.
So G is discrete here, so yeah. So for discrete G, I mean, it's, you know, a G gauge field really is just a choice of principal G bundle.
Okay, I think I know where it's located. Yeah.
Yep.
Sorry, I'm just trying to connect A, like what A is. So A specifies F. Is that why?
A specifies F.
Got it. Okay, thank you.
A specifies F, and it determines it uniquely up to homotube. And yeah, there's always one. Okay. So there's so far I've talked about unitary groups G. Let me tell you what the anti-unitary generalization is. Okay. Hopefully this will last. So for anti-unitary G, you know, so there are anti-unitary symmetries. So for anti-unitary groups. By anti-unitary group, I mean a group that might contain some anti-unitary elements. So how do I deal with that? So, you know, again, the intuition here is that an anti-unitary symmetry, like, you know, inversion in space or time reversal. Well, let's stick with time reversal. That's an orientation reversing symmetry on space-time, and so I would expect that in the field theory I should probe such theories with non-orientable manifolds, non-oriented, possibly non-orientable manifolds. So if I have a non-orientable manifold M, there's kind of a problem in defining this action in the naive way because, you know, this action, you know, if I think of this action as integrating, you know, getting a number from this degree D cohomology class, you know, it's really pairing it with the fundamental class on M, and when the manifold is non-orientable, you know, this fundamental class isn't well. So you have to define the fundamental class of this manifold more carefully. So basically, the fundamental class of this manifold lives in so fundamental class, fundamental homology class, fundamental degree D homology class. Is in HD of this manifold with Z coefficients that are twisted by the orientation bundle. What did I call the orientation bundle here? Let me call it C. I think Anton called it C. Okay, so what is the orientation bundle? It's just a Z2 principal bundle such that you know, it does a non-trivial twist when you go around an orientation reversing cycle. Okay, so that's the orientation bundle. And there is a fundamental degree D homology class, but it has to take values in not the integers, but the integers twisted by this orientation bundle. So so in order to then be able to you know, get an action, you would like to pair this fundamental degree D homology class with a sort of similarly twisted cohomology class. So the cohomology class that you pull back to M, you want it to be valued in U1 coefficients that are also twisted in the same way. Okay, yeah?
Sorry. What does it mean for the coefficients to be twisted by the bundle?
Yeah, so this is sort of a generalization of homology where you know, where these things don't take values in just the integers, but they take values in a certain bundle. I didn't define it, but it's just there so that non-orientable manifolds have so you can define a fundamental top homology class. I don't know. Is there a topologist who can explain it better?
I think you did a good job. It's in Wikipedia.
Yeah.
Twisted coefficients.
Twisted coefficients, yeah. Yeah, so it's just, yeah, instead of taking values in sort of the fixed integers, it sort of takes values locally in a fiber of a bundle that's sort of twisting around. Yeah. Anyway, so the upshot is that, this object here, the cohomology class that we're integrating, this thing that we're pulling back and integrating, better have, also take values in twisted coefficients. It's going to be U1 or R mod Z, similarly twisted by this orientation bundle. And the way that you can ensure that is by on the classifying space side of things, you can you can sort of put some extra structure on the classifying space side of things. So the classifying space BG, as sort of a topological space, it's just going to be the same as in the unitary case, but I'm going to put some extra structure on it. I'm going to put a Z2 principal bundle rho on it on BG, which twists every time you go around an element of pi1 of BG, which corresponds to an anti-unitary element. Okay, so that's sort of the natural twisting on the BG side, and I'm going to demand that the pullback by F of rho is precisely this orientation bundle. Okay, so if I do that, then given any x in now HD of BG with coefficients in U1 twisted by rho, given any cohomology class in the cohomology of this classifying space with these twisted coefficients that are twisted by rho, if I pull that back to M, I'm going to get, again, a class that's twisted, but twisted by this orientation bundle now, psi. Okay, and so that because that's twisted in the same way that the fundamental homology class is twisted, that allows me to get a well-defined action. Okay, so this is, I always found this endlessly confusing, by the way, so I'm sort of word this out carefully. This is written up in Anton's paper fairly nicely. Yeah. That's right. Homology or cohomology?
The homology.
No, the homology class is sort of given. There's a canonical one. What do you do with it? You use it. You pair it with the cohomology class to get a number. That's integrating. It's like the measure for integration. Yeah. Except when manifold's non-orientable, you have to be careful. That's why. Sort of a generalization. Yeah. So it's like the intuitive way to think about this is like, this when manifold is non-orientable, you go around this orientation reversing cycle, the sort of the measure, the dx, dy, whatever, changes sign, and so the thing you're integrating better also change sign in order for the whole thing to be well defined. That's kind of a pedestrian intuitive way of thinking about it. Well, I mean, physically so far, I'm just trying to define an action that's a function of a principal bundle. So this is, physically this is like integrating a local density in order to get an action. This is like integrating a local Lagrangian density to get an action. That's what this physically corresponds to. Yeah.
Do you know that there's always such a row?
Do I know that there's always such a row on BG?
Yeah.
Yeah. Yeah, I do. Yeah, so I mean the orientation reversing elements of G kind of have a Z2 grading on them, right? Because an orientation reversing element will square to an orientation preserving one, and so that's enough to sort of ensure this. Other questions? Okay. Let me see how much time I have. Okay, good. So right. So the upshot is this sort of allows you to formalize group cohomology classes at a field theory level, but it also sort of gives you intuition for how to perhaps obtain other more general actions that may correspond to the beyond cohomology phases. So so far basically what we've done is we've written down actions that correspond to integrating characteristic classes of just the bundle. And we hope that these actions somehow, in some vague way, correspond to putting lattice on space-time lattice models on space-time manifolds, integrating out the matter, and seeing what we get. But so you might just sort of ask, what other effective actions should in principle be possible? Like what other actions can you write down? And so the other sort of piece of data that you have, in addition to this principal G bundle, is that you have the tangent bundle on M, right? So the beyond cohomology. So what can we do with the tangent bundle on M? Well, the tangent bundle also has characteristic classes associated to it. And this is sort of a big subject. I'm not going to sort of enumerate all the various possible characteristic classes. I'm just going to talk about ones that are important for what I'm going to talk about, I guess, in the next 20 minutes, which are the Stiefel-Whitney classes. Okay, so these are classes Wi in Hi of M with Z2 coefficients. Okay, so these are cohomology classes which are associated to the tangent bundle in the same way that these group cohomology classes were associated to the principal G bundle, the gauge field. And so again, there's sort of the classifying space picture for these. So these can be obtained by looking at maps into the classifying space of these tangent bundles, but I don't have time to sort of discuss that whole story. But let me just sort of tell you some of the examples of these Stiefel-Whitney classes. So W1 is a very simple class. So this is a first cohomology class, and it basically tells you, given a cycle, whether it's orientable or whether it's orientation reversing or orientation preserving. That defines a cohomology class, first cohomology class with Z2 coefficients. Okay, so this is sort of a non-trivial such class gives you an obstruction to orientability. Tells you the manifold's not orientable. Okay, and then similarly, W2 in the higher classes can sort of similarly be defined as obstructions to certain things. So in general, the kth Stiefel-Whitney class is the obstruction to finding an n minus k plus 1 frame on a k skeleton. So like W1, for instance, is the obstruction to finding an maybe k plus 1 skeleton. W1 is the obstruction to finding an n frame on the 1 skeleton. So that's basically what it means to sort of, failure to have that is basically what it means to have an obstruction to orientability. Okay, but it's not going to matter too much what these things are. These are just some characteristic classes associated to this tangent bundle. They somehow tell you about how twisted this tangent bundle is. If the manifold is orientable, there's also these Pontryagin classes which are integer-valued cohomology classes in degrees that are integer multiples of 4. They're not going to play much of a role in what I'm going to talk about, but you just mentioned that they're there. In classes P sub k in H 4k of MZ for orientable manifolds. Okay, so we can just sort of play a game and try to construct actions out of these things. Okay, so for instance, even if I don't have, even my group G is trivial, so I just don't have any symmetry, I can construct an action out of these Stiefel-Whitney classes. So for instance, let me get a sort of exotic 4 plus 1D example. You can write down an action that's 1/2 integral W2, W3. Okay, so there's no group involved. There's just 1/2 integral W2, W3. That's one possible action you can write down. There's other examples that I'll discuss later. But sort of one realization that Anton had well, many people have had, but sort of in the context of SPT phases, is that look, these actions that you can construct out of, by multiplying various characteristic classes of the tangent bundle and integrating them, these actions are what's known as Cobordism invariants. So that ultimately sort of motivated him to just say, well, SPT phases are defined by all the possible Cobordism invariant actions that you can write down. But in order to for me to talk about that, let me just very briefly introduce the notion of Bordism and Cobordism. Okay, so Bordism. So for non-orientable manifolds, basically Bordism is an equivalence relation. I'm sure many of you have sort of seen this already, so I'm going to be quick about this. So these are D manifolds. The two are equivalent. Basically, they can be connected by one higher dimensional manifold. So the example that's always sort of drawn is this pair of pants where two circles, okay, these are or happen to be orientable, but the two circles are equivalent to one circle. If I write these two circles as M1 and this one circle as M2, then then they can be connected by this one higher dimensional manifold. So so just to formalize this, these are equivalent if there exists D plus one dimensional manifold X whose boundary is equal to M1 disjoint union M2. I'm glossing over all sorts of subtleties here, but yep.
Basically, or like the actions usually like represent something about the system, right? Like symmetries or like some interactions about the system. How is it that like writing down just an action with like say integral of W2, like what is that supposed to represent exactly?
Yeah, exactly. So this is an effective action after you've integrated out all the matter. So you've integrated out all the dynamical degrees of freedom, and this is sort of the effective action after having to put the system on some non-trivial space-time manifold.
So you can do this with any action, or like if you have like a standard sort of action for some QFT, you integrate everything out, all the fields out.
Yeah,
and you will get some invariance.
I mean, so this is something that can be done in principle, but so what I'd like to say is that I can take my not even just a QFT but a lattice model and just be able to put it on general space-time, integrate things out, and obtain this. I don't know how to do that in general, so I'm just kind of using this as an oracle, really, right? So we're gonna sort of use this as an oracle and try to on the lattice side reproduce mathematical structures which match the predictions of this oracle. That's the way I like to think about it. Yeah.
Integrating out the matter, does this depend on it being gapped?
Yeah, it certainly depends on it being gapped, absolutely. Yeah, even in this sort of fuzzy way of thinking about it, that's absolutely necessary. Okay, so there's a similar definition of Bordism for orientable manifolds. Everything has to be orientable. And I think I'd have to have the orientation reversed, but let me just, since I'm going to use this later, let me introduce this notation. So the equivalence classes in the non-orientable case, so this is the general orthogonal group of d-dimensional manifolds under this equivalence relation, is denoted by this. So these are the Bordism classes of non-orientable manifolds. And then there's a similar thing for orientable manifolds. Okay. And so there's also, okay, so this is just sort of just considering the tangent bundle alone, like what kind of characteristic classes can you have with just a tangent bundle? And so, right, so what is true in this sort of limited case of just trivial G, just a tangent bundle, is that in the unoriented case, the Cobordism class of a manifold is determined uniquely by these so-called Stiefel-Whitney numbers, which are just kind of integrals of this form. So if you sort of compute all the Stiefel-Whitney numbers of a given manifold, that determines the Cobordism class uniquely. In the orientable case, you have a restricted set of manifolds because now they're required to be orientable. You have a restricted set of Cobordisms because the Cobordisms themselves are required to be orientable, so it's sort of a different thing. And in that case, it turns out that the oriented Cobordism classes are also determined by Stiefel-Whitney numbers plus Pontryagin numbers. Okay, so that's nice. That's sort of nice because it just means that if physically you just want to consider all actions that you can make of this form, that's really the same thing as considering maps from these Cobordism groups into U1. It's the same thing in this limited case without any symmetry groups G. So these kinds of actions. Did I write this here? Yeah. So the case. Let me first talk about unitary G. So for the case of actually. Oh, sorry. I needed to introduce one more thing. Right. So for the case of no symmetry group, these actions are just given by maps from these Cobordism groups into U1. That's just sort of follows from the fact that these Stiefel-Whitney numbers, and in the orientable case, Pontryagin numbers uniquely determine the Cobordism class. So with non-trivial G, it turns out that there's a sort of enrichment of this notion of Cobordism to include non-trivial principal G bundles as well. So in other words, if you have a space-time manifold M that now also has a principal G bundle, and another one that also has some other principal G bundle, there's a notion of Cobordism between them. And I'm not going to write out the formal definitions because I don't have time, but basically it's just a manifold X with an interpolating G gauge field. Okay, so the G gauge field is equal to the initial one on M1 and the final one on M2. So there's enrichment of the notion of Cobordism to manifolds with principal G bundles, and so with G symmetry, you have sort of the notation is omega SO D of BG. So that's in the orientable case. In the non-orientable case, it's omega O of D with BG. And here, there's an extra requirement relating to the stuff that I talked about for non-unitary symmetries, which is just that if you think about your gauge field as a map into BG, there's this requirement that it pull back the sort of canonical twisted bundle on BG to the orientation bundle on whatever manifold you're interested in. Yeah.
So what is the condition on the higher dimension of manifold interpolating between them such that you think of it as a G symmetry?
Oh, so the higher dimensional manifold just has to have a G bundle on it,
Okay.
and that G bundle has to restrict to the ones that you already have on M1 and M2. Yeah. Okay, so now, so I've sort of finally gotten to Anton's proposal. So the proposal is that, so this is this Cobordism classification proposal, is that in the case of unitary G, SPT, well, so there's a subtlety, so let me not call it SPT phases yet. SPT actions, the actions that you can get by integrating out matter, correspond precisely to the homomorphisms of SOD BG into U1, and in the non-unitary G with some non-unitary elements, the correspondence is ODBG U1. Okay, so formally this is kind of like all actions that you can construct out of characteristic classes of both the bundle, the principal G bundle, and the tangent bundle. Okay, but it's just kind of an independent proposal. So like, okay, this is like a hypothesis. This is, So what you can check is that all the group cohomology phases, the actions that you get for that are determined by these characteristic classes of just the G bundle are Cobordism invariant. So sort of everything that we know fits in here, and this extends the sort of group cohomology proposal. So all group cohomology actions are part of this Cobordism classifications, but there are also some actions here that involve these Stiefel-Whitney numbers that are not in the group cohomology proposal. Yeah. Sorry, was there a question? No. Yep.
So I understand you're writing actions, but what was the argument that action written this way are SPT rather than you might have some other cases?
Again, you treat this as an oracle. Like operationally, by itself, this doesn't tell you anything about gap lattice systems, or that doesn't tell you anything about Hamiltonian systems. You treat this as an oracle. You ask, how many phases should I expect in a given dimension? Then you go back to the lattice system, and you start over from scratch, and you try to define invariants that reproduce that.
So there's no argument like this is a short-term thing?
I mean, I think ultimately one would want such an argument, but I don't think that in general one can sort of, for general lattice models, it's not obvious how to connect. Okay. Yeah.
In your introductory example from the manual talk,
yeah.
The tangent bundles were trivial because you were talking about a torus and
yeah.
R3. So you were only talking about characteristic classes of the principal bundle.
That's right.
But now you're suggesting a hybrid. You're allowed to build
yeah.
from characteristic classes of the tangent bundle and the principal
yes,
bundle,
right.
mix them together. The only restriction is they should go into the top class so that you can
yeah.
integrate them and get a number.
Absolutely. Yeah. And in fact, there's an example in 4+1D that Matt and Jengwon and I worked out where the action is integral of a W2 squared. This is over 5 manifolds. This is a certain beyond cohomology phase that has a kind of nice interpretation. Okay, so there's one sort of subtlety that I didn't really talk about much. I said SPT actions, not SPT phases. So the fact is that in the oriented case, when this is omega SO, this Cobordism group, in addition to having sort of torsion, it might have some free factors, some copies of Z. And if you look at the homomorphisms from Z to U1, that's basically another copy of U1. And that's sort of a connected class of, those SPT actions are all sort of connected to their trivial action. So it's not correct to say that this homomorphism group is the set of SPT phases. It's rather that the connected components of this group give you SPT phases. So this is related to something called theta terms, sort of continuously tunable theta terms in effective actions. So really, SPT phases in the unitary case are classified by the homomorphisms from the torsion part of this Cobordism group into U1. But that's a subtlety that I just wanted to get out there. Okay, so I'm out of time. So unfortunately, I don't have time to tell you about what I think was actually sort of the most interesting thing that I hope to talk about, which is, how is any of this reflected on the lattice side? So let me maybe just briefly say it in words for a few minutes, but I'm not going to have sort of time to do it in detail. But in words, the idea is as follows. Okay, so how so this gives you an enrichment of the cohomology classification. It gives you extra phases. There's extra phases predicted here. How do we see these? How do we probe these on the lattice side? So QCA mentioned at the end of her talk this proposal by Else-Nayak. Maybe I'll just write down the reference because I think this is a really nice paper. Let me just at least write down this reference. So Else-Nayak, PRB 90. So this is a paper from 2014, where they showed how to extract, for a general group cohomology phase, how to extract the group cohomology class from the lattice model. This is entirely lattice construction. And the essential idea is that, given a group cohomology, given a Hamiltonian that is supposed to describe a system in an in-group cohomology phase in D dimensions, what you do is you construct a sequence of operators in lower and lower dimensions. So she illustrated this in the case of the Z2 SPT in 2 dimensions, where there is initially everything was happening in 2 dimensions, then she found an effective action on the 1-dimensional boundary, and then she truncated that, and there was something happening at endpoints. So there's this kind of sort of descent procedure. And in this paper by Else-Nayak, they described this descent procedure in general. So starting in d dimensions, it turns out that you can sort of keep going down in dimensions, and at the end of the day, you end up with a function, a U1 valued function of d or d plus 1, however many group variables to define the appropriate cohomology class. This is how you extract the cohomology class of an SPT phase in the context of the lattice. And they argued that sort of this whole construction is independent of the various arbitrary choices that you make. So this is a good quantized invariant. Okay, so how do the beyond cohomology phases fit into this kind of prescription? It seems like this kind of prescription sort of always spits out a cohomology class. So what's happening with the beyond cohomology? Like supposing we started with a beyond cohomology Hamiltonian. So based on a couple of examples that my collaborators and I have worked out for both the 3 plus 1 dimensional Walker-Wong models and certain phases in higher dimensions, we think that basically this is related to QCA. So what happens is for the beyond cohomology phases, this Else-Nayak procedure at some point becomes obstructed. And the way it becomes obstructed is, in this Else-Nayak procedure, in order to keep going down in dimensions, you have to truncate certain unitary operators. And these unitary operators are sort of always, by construction, guaranteed to be locality preserving, but they're not necessarily guaranteed to be finite depth circuits. So the basic thing that we think happens is that these beyond cohomology classes are reflected in non-trivial QCAs appearing in this Else-Nayak construction. And we sort of say this on the basis of like 2 examples that we've thought about. So it would certainly be sort of nice to sort of go deeper and try to make this connection tighter somehow. But since I don't have time to explain those examples, let me just end here. Thanks.